Hey everyone, I am Miss Hooke, your physics teacher. In this video, we'll be going through the effects of forces on an elastic object, specifically linked to Hooke's law. So what we'll be covering in this lesson are elasticity, the relationship between force and extension of a spring, calculating spring constant and elastic potential energy, as well as the factors which affect spring constant. So yes, spring is in the air. Right, moving on. Okay. First of all, let's go through the properties of materials. Now, when we talk about an object being elastic, there's a very common misconception that a lot of people have is that something that's elastic can stretch. I'm just going to maximize this first. All right, so when we talk about an object being elastic, like a rubber band, people always associate elasticity with objects that can stretch like a rubber band because, yes, a rubber band is elastic, but that's where the most common misconception is. You see, an object that's elastic, like a rubber band, can stretch. So this is not elasticity, this is actually the stretchability of an object. When an object is elastic, it means it can return to its original shape and size after the force applied on it has been removed. So you can see how when we stretch a rubber band and when we let go, it's able to return to its original shape and size. So elasticity is the property of an object where it's able to return to its original shape and size after the force applied on it has been removed. So a rubber band, once you stretch it and you let go of the force, it's able to return to its original shape and size. So that's being elastic. Another very common object that's elastic is a spring. In this video, we're going to be focusing on elasticity, but for the sake of understanding the properties in completeness, I'll just touch on plasticity as well. Plasticity is the ability of an object to maintain its original shape and size after the force applied on it has been removed. An example of this is plasticine, which is why it's called plasticine. It's named after the plasticity property. So plasticine, or in other terms modeling clay, are perfect for making shapes because if you were to press and mold them into different shapes, they retain the new shape. So that's why they're great for modeling. So for example, if we take a closer look here, I don't actually have plasticine, but I do have some white tack. So you can see that if I press on this white tack, it keeps its new shape, as opposed to a rubber band, which when you stretch it and you let go, it goes back to its original shape and size. So that's elasticity and plasticity. So these objects are elastic while these objects are plastic. We only need to focus on elasticity in this lesson. At least now you know the opposite end of the spectrum is being plastic. So to learn more about elasticity, we're going to be using a spring because a spring is easy to measure in terms of its length as compared to a rubber band. So based on that, let's learn about the relationship between force and extension of a spring. Now, as you can see, when force is applied on a spring, we find that the greater the force applied, the greater the extension of the spring. So the extension here means the lengthening of the spring. The spring gets longer, so the spring is extending. Note that this also applies to the compression of a spring. So to compress a spring means you have a spring where the length becomes shorter because we apply a force inwards to the spring instead of pulling the spring outwards. So to study the relationship between force and extension of a spring, we would do an experiment involving a spring. So if you're studying this in school, you should get to do this experiment. If you are learning this at home, what you can do is you can go and buy a spring and do this experiment on your own at home. The experiment is really quite simple. If you'd like a demonstration on how the spring experiment can be conducted, I do have a video that shows how to conduct the experiment with the spring and how to take the measurements. The link is shared in the description below. So generally the experiment is like this. We have a spring which we hang from a retort stand so that it's hanging freely. We hang a weight where the value of the weight is known. So you do need to know how much weight you have hung on it. So for example, if you're hanging 100 Newton or 200 Newtons, it has to be a known weight so that we can compare the weight against the extension. To measure the extension, we would use a meter rule. So the meter rule has to be placed parallel to the spring so that we can measure the length of the spring clearly based on the meter rule. Now, when we conduct the experiment, you will find that the more weight we hang on the spring, the greater the spring length would be. And based on the data of the experiment collected, if you were to plot a graph, you would get a linear graph that looks just like this. So on the x-axis, I've written here load or force or weight because it depends on the questions and how they phrase what should be on the graph. So the load here means what we're hanging from the spring. Sometimes we measure the force instead, or we want to get the weight of the object we're hanging from the spring. All of these are measured in newtons, and they're kind of the same thing in the sense that they're all a type of force. That's why we'll find the relationship to still be the same. Obviously, this graph will not start from the origin because even if you don't hang any weight or apply any force on the spring still has a spring length. So you'll find that from this graph, the y-intercept here is the original spring length. And as we add more weight to the spring, we'll find the spring length increases in a linear fashion. Now in physics, we do like linear graphs, and what we like even more are graphs that show a directly proportional relationship. That means if possible, we want this graph to start from origin. So how do we get this graph to start from the origin? We need to minus the spring length so that graph would move downwards. So this term is known as the extension, where extension refers to the difference between the new spring length and the original spring length. That means how much extra the spring has extended by. So that's the extension. So if we were to get the extension instead and put that in a graph, now we'll get a directly proportional relationship. Now, the person who discovered this relationship is called Robert Hooke. And obviously, this discovery would be named after him. And that's why it's called Hooke's law. So Hooke's law states that the extension of a spring is directly proportional to the force applied, provided that the elastic limit of the spring has not been exceeded. Now, what does this mean? If you know anything about springs, you'll know that the spring cannot stretch indefinitely. There's a certain limit to which the spring can stretch before it would start to spoil permanently. So to show you an example of a spring that has deformed permanently, both springs were identical originally, but you can see the spring on the right has deformed so badly, it's been stretched so much so it cannot return to its original shape and size. This spring has been deformed as a result of my students putting too much weight on it when they were doing the spring experiment. And as you can see, the deformation is now permanent. Yes, this is what it originally looked like, and this is what the spring looks like now. So once it has reached this stage, the spring cannot be saved. That means it is already spoiled. You cannot use this for any more experiments. It will never return to its original shape and size. So now I only keep it as an example to remind students, please don't hang too heavy weights on the spring. So when we talk about Hooke's law, it only applies as long as the spring has not deformed permanently. Once spring has deformed, like what you saw just now, you'll find that you can continue to use a spring, yes, but you'll find that it no longer obeys the law. That means the relationship is no longer proportional as it is at the beginning. So actually from a certain point onwards, you'll find that the spring can no longer be used. Now we'll only learn about the spring deformation and what happens to the spring at higher level, like A levels onwards. For those of you who are taking SPM and IGCSE, we'll only focus on the relationship up to the point before it is deformed. So if we look at Hooke's law states the extension is directly proportional to the force applied, provided elastic limit of the spring has not been exceeded. And if it has exceeded, yes, the graph will start to show a curve. Now, sometimes you may get a graph where they flip what's on the x and y axis, where they put the load, force, and weight on the y axis instead, and extension on the x axis. When you look at this kind of graph, you'll find that, oh, that's strange. It shouldn't be this way because it's not following Hooke's law. And for another, if you were to conduct the experiment, the independent variable on a manipulated variable is the weight that we're hanging on the spring. So that should go on the x-axis. Whereas the dependent variable or the responding variable is the extension, which we're measuring on the spring. So that should go on the y-axis. So when and why would they give a graph where they flip the variables on the x and y axis? It comes down to the calculation, which I'll show you shortly. So if you're given this graph, you can see how, because the x and y axis have been flipped, obviously the graph cannot be following the same curve. So that's why it curves the other way. It's like a mirror image of this graph. Now, I know I keep mentioning the point of deformation, and you can see in Hooke's law, they talk about elastic limit, but the elastic limit is not labeled on the graph here. And the reason why I haven't labeled it on the graph is because for different syllabi, the elastic limit is marked differently. Why? Because there's some slightly different interpretation in different syllabi. I'm only going to cover this for SPM and IGCSE. In both of these syllabi, the graphs would look the same. It's just that the position where we mark the elastic limit is slightly different. So if you're taking SPM, the elastic limit is the maximum point where the graph is linear. That means if you're given this graph, look at the graph and find where the maximum point of linearity is. How you can find it is by placing a ruler, follow the line of the graph, and you'll find that the graph will start to curve away from the line after a certain point. So look for the highest point where the graph is still linear and mark that point. That point is the elastic limit of this graph. So you can see how Hooke's law is very true in this case. The extension is directly proportional to the force up to the elastic limit. If you're given this graph, it's actually exactly the same. It's just that it curves in the opposite direction. So the elastic limit is still the maximum point of linearity. This is the elastic limit. Now, if you were taking IGCSE, the maximum point of linearity is actually known as the limit of proportionality. So how do we get the limit of proportionality? Just look for the maximum point where the line is linear. So you take your ruler, place your ruler in such a way that it follows the line of the graph, and you'll find that the graph will start to curve away from the line. At the highest point where it's a straight line, that's the limit of proportionality. So what does limit of proportionality mean in this case? Proportional means that the graph will show a straight line. So limit of proportionality means the limit where the graph is linear. So that's why the limit proportionality is the highest point where the graph is linear. So whether they give you an extension load graph or a load extension graph, the limit of proportionality would be the maximum point where the graph is linear. So for IGCSE, they will only ask you to identify the limit of proportionality. They won't ask you to identify where the elastic limit is. Why? Because the elastic limit depends on the spring. So the elastic limit is normally at a value that is slightly higher than the limit of proportionality. So if you have a spring, you'll find that this is the maximum point where it starts to be linear. Can it still stretch a little bit more? Yes, it can. If you stretch it a little bit more, you find that when you remove the force, it can still return to its original shape and size. It hasn't gone through permanent deformation yet, but it's reaching the maximum point where it can stay elastic. So if you stretch the spring beyond that maximum, that's when the spring would permanently deform. So between the limit proportionality and the elastic limit, you'll find that yes, there is a very small value where the spring no longer follows the relationship of directly proportional, but the spring can still return to its original shape and size. So the elastic limit and the limit of proportionality are not the same point on the graph for IGCSE. The elastic limit is slightly higher, but again, how much higher, it depends on the spring. So that's why in IGCSE, they will not ask you to identify where the elastic limit is, because it's not a point that is easy to determine. So they'll only ask you to identify the limit of proportionality. Just be aware elastic limit is normally slightly higher, but you don't need to know how much higher. Alright, so now let's talk about spring constant. So what is spring constant? So the spring constant here just refers to something like a coefficient or a value that is associated with the spring's ability to extend. The definition of spring constant is the force per unit extension. The definition is actually derived from the formula, but because I've given you the definition, I'm going to write the formula out now based on the definition. So the spring constant is the force applied per extension. The formula is normally written in symbol form. So the symbol for spring constant is K, force is F, and extension is X. Now, even though it says here extension, you can keep in mind that if it was compression, that means the difference of the original spring length to the new spring length where it's compressed, it's also the same calculation. So instead of using X as extension, you can use X for compression instead. So I'm going to write here, this is also possibly compression. The unit for spring constant depends on the question, but generally it's like this. If force is in Newton and extension is in cm, the spring constant value would be Newton per cm. Sometimes you might be given the value of extension or compression in millimeters, so then this could become Newton per millimeter. If you need to write this in SI unit, then extension should be in meters, which means it should be Newton per meter. So all of these are accepted units of the spring constant. You might find in some questions they don't call it spring constant because they may be using other elastic objects like a rubber band. So in those cases, they're called force constant or elastic constant. The way you calculate it is the same. So to understand spring constant, basically it means how much force needed to extend the spring. The greater the spring constant, the more force is needed to extend the spring. For example, if you're comparing 1 Newton per cm against 2 Newton per cm. 1 Newton per cm means you only need 1 Newton to extend 1 centimeter of the spring. 2 Newton per cm means you need to apply 2 Newton of force to extend the spring by the same 1 centimeter. The greater the spring constant, the stiffer the spring, the harder it is to extend. So yeah, sometimes you might come across the term stiffness, and in this case it means the same thing. So I'm going to write here on the side as a note that this is sometimes known as a force constant, elastic constant, or stiffness. For example, spring stiffness. So just be aware of these different terms because they mean similar things, and you can use the same formula to calculate any of these. Now, when you stretch or compress a spring, the spring will store elastic potential energy. So elastic potential energy is potential energy stored as a result of deformation of an elastic object such as a spring. When you compress a spring or when you stretch a spring, when you let go, that spring bounces, converting that potential energy to kinetic energy. Now, this is only covered in the SPM syllabus. It has already been taken out of the IGCSE syllabus. So those of you who are taking IGCSE, you don't need to know this formula. To calculate the elastic potential energy, the formula is E equals half Fx, where E is the elastic potential energy, F is the force applied, and X is the extension or compression. The unit for elastic potential energy is the same as the unit for all energy. It's measured in joules. Now, if you were to calculate in joules, then you have to make sure that you are using SI units for all the other variables. So force must be Newton, and extension or compression must be in meters. You cannot use centimeters or millimeters in this case, because if you want to write this in joules, they must all be in SI unit. That's because 1 joule is equivalent to 1 Newton times 1 meter. Now, sometimes you may be required to combine this elastic energy with the spring constant formula. So we already know from the previous slide that K equals F over X, which can be rewritten as F equals Kx. We can take this and substitute it into this formula, forming a new formula. So we have E equals half. Instead of F, we will write now Kx times X, and this gives us half Kx squared. So you can use this derived formula if you don't have the force applied, but you have the value of the spring constant. Just realized that my face was blocking the formula, so here it is. Now, you may also be required to know how to get those values of the spring constant and the elastic potential energy from the graph. So if you're given an extension load graph like this, how do we get the value of the spring constant or the elastic potential energy? Let's start first with the spring constant. So we know that the spring constant can be calculated as K equals F over X. So when you look at this graph, you'll find that the extension is on the y-axis and F, which is the force, is on the x-axis. Let's try out the gradient. So the gradient, as we know, is rise over run, or y2 minus y1 over x2 minus x1, which is essentially is y over x. That means the gradient is actually the extension, which I'll write as x, divided by force. As you can see, the gradient and k are actually inverse of each other. If we rewrite this formula to try to get what's on the right hand side to be the same, we would get 1 over k equals x over f. So now you can see these two are the same. Therefore, we can conclude that the gradient will give us the value of 1 over k, or 1 over spring constant. So if we wanted to calculate the spring constant of k, we just need to get 1 divided by the gradient. And if we wanted to calculate the elastic potential energy, we know that the elastic potential energy can be calculated as E equals half Fx. And if you look at the graph, you can see how this half Fx is actually same as calculating the area of a triangle, which is also the area under the graph. So what this tells us is that the elastic potential energy is equivalent to the area under the graph. So if you wanted to calculate the elastic potential energy, we just calculate the area under the graph, and that would give us the value of the elastic potential energy. Now, this is for the extension load graph. And remember that I mentioned earlier that sometimes we may be given a load extension graph instead. So why? Now, let's take a look why. Again, let's start off with the spring constant. So we know that spring constant is K equals F over X. If we wanted to calculate the gradient of the graph, remember that gradient is basically y over x. So y is what? Force, and x is the extension. You can see from these equations that the spring constant is actually equal to the gradient. We don't have to do any inversion or additional calculations. So this is the reason why sometimes in some questions they give us load or force or weight on the y-axis instead and extension on the x-axis, even though based on the experiment results and based on Hooke's law, by right extension should be on the y-axis and force on the x-axis. But because of this calculation, they do make some allowances by making some changes to what's on the x and y-axis, so that it's much easier for us to obtain the spring constant. So if you're given a graph for the spring, do be very careful. Check what's on the x and y axis and work out carefully what the gradient is equivalent to. For the elastic potential energy, it's pretty much the same thing because elastic potential energy is still E equals half Fx. So whether it's extension load or load extension graphs, you will still find that the elastic potential energy is the area under the graph, whichever graph you are given in this case. So again, reminder, if you're given a graph, do check what's on the x and y axis and make sure that you do your analysis based on the correct values of the gradient and area under the graph. Now, let's take a look at the factors affecting the spring constant. So in this case, this means if we have different springs, or if we want to try to modify a spring, how can we increase or decrease the spring constant? So this topic is only covered in SPM, but if you're taking IGCSE, no problem for you to learn. There are 4 factors. The first factor is the length of the spring. That means if everything else is the same, that means the material and the diameter of the coil and everything else is just the length of the spring. If you have a shorter spring and a longer spring, try to visualize and think, which spring do you think is easier to extend? So the longer spring is easier to extend, right? So in this case, that means the relationship of this factor is that when the length of the spring increases, I'll just write here length, when the length increases, the spring constant decreases because it's easier to extend. That means you need less force to make the spring become longer. The second factor you need to be aware of is the diameter of the coil. So diameter of coil here refers to the coil itself. So like comparing a small spring against maybe a large slinky spring, for example. So if you have a small coil or a large diameter coil with the same length, try to think, if you have a small spring or a large slinky spring, which one is easier to pull and extend? The slinky, right? So the greater diameter of the coil, because the materials are further away from each other, that means there's less force needed to make them extend. So the relationship here is that when the diameter of the coil increases, the spring constant decreases. The third factor you need to know is the diameter of the wire. So in writing diameter, do be very specific. Are you referring to the diameter of the coil, which means the diameter of the coil like so? Let me just label it clearly. So the diameter of the coil like this, in measured with the purple double-headed arrows. Or are you referring to the diameter of the wire? That means the wire diameter itself. Sometimes this might be called the thickness of the wire. So just to let you know, in the older syllabus of SPM, the term thickness was not accepted because round cross-section objects do not have thickness. Thickness is supposed to be uniform, like the thickness of a piece of wood. But I have noticed in the newer syllabus, including in your textbook, they do mention thickness of wire instead of mentioning the diameter of wire. So I've included this term in here, just in case you come across this in your exam papers, and you'll know what thickness refers to. Do be flexible though, whether it's diameter of wire or thickness of wire, they both mean the same thing in this case. So you could have a thin wire. Let me make sure I draw my spring away from my face so that my face is not blocking. Okay, that's a terrible drawing. Let's try that again. Or it could be a wire that's much thicker like this. Let me use this pen. So now I want you to think, if you have a thin wire or a thick wire, which is easier to extend? Yes, the thin wire in this case, the lower diameter. So if the diameter or thickness of wire increases, the spring constant increases. So that's why when we talk about diameter, you do have to be very specific. Are you talking about the diameter of the coil or the diameter of the wire? Because as you can see, they're both different properties and have different effects on the spring constant. The fourth factor, of course, is related to the material. So there's no relationship here to speak of because different materials have different strengths. For example, if you have a copper spring versus a steel spring, obviously the steel spring is so much stronger, therefore it has a higher spring constant. So for this case, I will not write out the relationship. So just be aware, though, that materials can affect the spring constant. And also you do need to be aware about concepts of series and parallel arrangements. So when you have multiple springs and you hang them in series, that means you hang them one after the other and the object is hung from that series of springs. If you hang the springs in parallel, that means you hang them side by side like this, and the weight of the object is being shared across the different parallel springs. Now, do you need to be able to solve questions? Yes, but I'll share with you how to solve questions in separate videos because there are different types of questions for the different syllabi. So for example, in SPM, not only must you know how to do the calculations for the spring, constant, and elastic potential energy, you will also need to know how to solve questions involving series and parallel arrangements. For those of you who are taking IGCSE, you only need to learn how to use the spring constant formula. You won't be required to solve complex questions such as the different types of arrangements of the springs. So that's why I'll be putting them in different videos for the different syllabi. And that is it for this video. So if you found this video educational and helpful, please click like and subscribe to get more free physics lessons. Do check out my YouTube channel for videos on other topics which you might find helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's at ko-fi.com/physicsrocks. If you'd like access to notes, quizzes, and syllabus updates, do visit my website at physicsrocks.com. Happy studying!